Okay, our next speaker is Jeffrey Reed, a research chemist from Army Research Laboratory Adelphi site. He will be speaking on advanced battery chemistries, fast charge batteries, and lithium-ion capacitors. Jeff, whenever you're ready, take it away.
All right. Hi, everyone. I'm going to talk today about some of our work on the advanced battery chemistry team. I'm not going to cover everything that we do here in the electrochemistry branch, but just touch on a few specifics, give you a flavor for the kind of work that we do here in Adelphi. So our team is made up of mostly chemists, some material scientists, and chemical engineers, and a lot of the work that we do is really materials based. So we're developing materials, we're studying new materials. We do a fair amount of work in electrolytes for lithium-ion batteries and other battery chemistries. So on my team specifically, the advanced battery chemistry team, we do a fair amount of work on single ion conducting ceramics, and that's headed up by Jeff Wolfenstein and Jan Allen. And they've worked on different solid electrolytes over the years. The one that they've currently focused on is LLZO. They've worked on trying to densify that material, improve conductivity, and then interface it with various anode and cathode materials to make solid-state batteries, lithium-sulfur batteries, that kind of thing. So that work is ongoing. We've done a fair amount of work in rechargeable lithium metal systems. So Chemistries Zhang has done a lot of work on lithium-sulfur batteries. So if you're familiar with that field, he's published a lot of different approaches to try to improve that technology to the point where it could be used in a commercial application. So fairly recently, we've started to look at dual graphite batteries. I'm involved with that, and we have a postdoc who worked on that. And basically, that's anion intercalation materials. Like I said, one of the specialties we have here at ARL is electrolyte work, specifically high voltage electrolytes. And the dual graphite system is a high voltage system. So it gave us an opportunity to develop some electrolytes for that system, and also to study some of the fundamentals of it. And then what I'll mainly talk about today is hybrid lithium-ion capacitors or fast charge batteries, some of the work that we've been doing over the past couple of years on electrolytes for lithium-ion capacitors and pre-lithiation techniques for lithium-ion capacitors, and then where we think that will be going in the future for the Army. So fast charge batteries, if you've worked with the Army before or seen the kind of work we do, it's all a lot of what we've done in the past is really focused on high energy density batteries. So the main goal of much of the work that's gone on here at the Army over the past 20 or 30 years has been to try to improve the specific energy of batteries, both primary and rechargeable, because soldiers have to carry batteries, and they have to carry a lot of batteries. So, our work has always been on new materials. We've done a lot of work on both primaries and more recently high voltage lithium-ion batteries, and most of that work is really focused on trying to improve specific energy, right? So how much it weighs for how much energy. There's limits to what can be done there, obviously, and so we're thinking about a new approach, and that's really offloading some of that energy to other systems, and to do that, you need fast charge batteries. So the idea is that you have in a soldier or squad unit, you'll have sources of energy, which might be generators or fuel cells or whatnot that are not at the front line, and you have a way to move that energy quickly to the soldier, so he doesn't have to carry all the batteries with him. So That's the concept, and to have that concept work, fast charge batteries really have to be something that's available to move that energy around. So what we look at now is, if you look at what's currently available, you look at high power LFP, lithium iron phosphate batteries. They're about 90 watt hours per kilogram. You can charge them in an hour or so. What we're really looking to is a fast charge battery that can be charged in 5 or 6 minutes. And this will allow for energy to be moved around a squad. It'll be allow for energy to be transferred from a source location to the soldier. And it would also allow for energy scavenging to occur quickly when the soldier is moving. So in the short term, 2025, we're hoping to get to a fast charge battery at 80 watt hours per kilogram. And in the future, beyond then, is to try to get to something that's comparable in energy density with what the soldier carries today, the 2590, which is about 150 watt hours per kilogram, but at a very fast charge rate. So what this concept does essentially is it offloads the energy from the soldier to another system, and allows for the soldier not to have to worry about where he's going to get his energy from, and lightens his load, which has always been a major goal of our efforts here at the Army Research Lab. Now, programmatically, how this fits into the larger picture is the Chief of the Staff of the Army has some priorities, and in terms of how fast charge batteries and this concept fits, it mainly fits into what would be considered soldier lethality. So extending soldier missions, so he can be out for 3 or 4 days or up to a week, will improve the lethality of soldiers. So that's where it fits into the larger picture of what the Army's trying to do. Now, in the short term, and by short term I mean 2025 or so, there's certain things that we can do to achieve this fast charge battery. There's basically 3 approaches that you can take. The first approach is adopting a anode that is similar to what's used in a lithium-ion capacitor. So in a lithium-ion capacitor, normally what you do is you have a hard carbon anode, and it is oversized significantly. So normally the amount of anode in there is maybe 3 times what you would normally have in, say, a lithium-ion battery. And it's a hard carbon, so hard carbons tend to accept charge very rapidly. And so one approach is to design a lithium-ion battery with an anode, a hard carbon anode, which has a large capacity. The second approach is to change the type of anode material that you use. So if you can use lithium titanium oxide, LTO type materials, or other newer anode materials that allow for fast charge, and that's an approach that's been taken by certain battery manufacturers, and that again allows for fast charge in the order of minutes. Okay, and then the third approach is really looking at new electrolytes for that will allow for fast charge acceptance at graphite anodes. That's the most preferred approach, but also probably the most difficult approach. So, in the longer term, the approach to get higher energy density is really to go to a 3D battery. And what does that really mean? That means that the diffusion lengths for lithium-ion transport need to be very short. And so the ability to, which if you look at conventional technology, what does that really mean? That means removing all of the porosity from the cell and shortening up the distance between anode and cathode material. So in the long term, I think that's where we will be working. And that should allow us to develop fast charge, high energy density batteries. And again, in the short term, we're thinking, prototypes type technology will be based on either lithium-ion capacitors or something like the Toshiba type technology, where you have a different anode, which allows for fast charge acceptance. And then in the long term, 3D prototype cell technology. And this really is going to involve developing a new way to manufacture batteries. So right now, most batteries are made using, or all batteries are made using slurry coating techniques. And the problem with that is, of course, that you have electrode porosity and you have macroscopic distances between your anode and cathode. And when you look at any of these, what people would call 3D batteries, what they really are is they're batteries that have very short diffusion lengths for in this case, lithium ion. So when we look at that, we see that most of the technologies that are out there that produce 3D batteries aren't really scalable to large kilogram type batteries, which the Army uses. So a new technology, a new manufacturing technology needs to be developed. This slide just shows you where lithium-ion capacitors lie in the sort of the energy power spectrum, and I'm sure you've all seen this chart before. I'm going to talk a little bit about some of the work that we've done in lithium-ion capacitors. Again, just to give you a flavor for it. We've looked at several things. One of the things that's very important in lithium-ion capacitors is that because you put in a very heavy anode, you have to pre-lithiate the anode. There's no way around that, really. So unlike a lithium-ion battery where you build the cell in a balanced format, in a lithium-ion capacitor you really need to pre-lithiate it. So the problem with that, of course, is that it adds a significant cost to the process, and also it's not necessarily that uniform the way that it's done. So I'll talk a little bit about some of the work we've done there, and then a little bit about electrolyte and additives for lithium-ion capacitors, trying to improve the high-temperature performance of these systems. So again, this is just the outline of the work that we've done. We've also started to look at hybrid systems, so trying to hybridize both lithium-ion capacitors and lithium-ion batteries to get some more energy out of that system. So if you look at pre-lithiation of the lithium-ion capacitor for a hard carbon anode, there's basically three ways to do it. You can use SLMP, which is the stabilized lithium metal powder. You can spray that on your electrode. You can use lithium foils, which you just lay on the electrode, and then you build your cell and you add electrolyte and you wait. And so it takes some time for this process to occur because you're basically just contacting the anode with mechanically with the lithium strip. And there's some non-uniformity. If you look at the pictures there, you can see it's not a uniform process. So the third approach is to have a sacrificial electrode, so you can have a third electrode essentially, a lithium metal to lithiate that hard carbon. But again, all of these techniques add cost. So we thought about different ways to approach this. And one approach that Sheng Zhang came up with was to actually use lithium sulfide. So in this approach, what you basically do is you're putting lithium sulfide into the activated carbon electrode. And then when you charge up the cell initially, you decompose the lithium sulfide, form some lithium sulfate and lithium metal. The sulfur bonds to the activated carbon and essentially becomes inactive. And the replacing some of the oxygen functionality that's on the activated carbon. Most activated carbons have a large content of oxygen in them, somewhere around 5 to 10%. So this approach works pretty well. This just shows that at 15 weight % lithium sulfide, you're basically able to, if you can read this chart here, you can see on the right, you've lithiated your graphite electrode, and you're able to cycle the full cell pretty well. So this approach, again, allows you to do the pre-lithiation, and you don't have to. It would be a lower cost approach to forming an LIC.
I'm
Yes.
for most of it, but.
And this just shows cycling here. Now, the one drawback of this approach is that it limits your voltage range for cycling. But for a typical LIC, you're going to cycle up to about 3.8 volts. And so at that condition, the performance is as expected. And then I'll talk a little bit about some of the electrolyte work that we've done. So we've looked at a variety of different additives for the lithium-ion capacitor. And most of our testing has been done in ECDMC and ECEMC, which are sort of the standard electrolytes for this. And this just shows for different additives how the rate performance looks. And then the next chart here, again, based on the additive, we get different performance. And in this particular case, the TMSP additive performs the best. Here we're doing float testing, so the sort of the standard test for LICs is to hold the voltage at the upper charge voltage. So in this case, it's 3.8 volts for 120 hours, and then do some cycling, and then repeat that process multiple times. And here, this just shows with the additive TMSP, we get some better performance. Here we're floating at 65C and then cycling at 25C, and again, you can see some benefit from additives here, TMSP. Again, I mentioned some of the work that we're doing is looking at hybrid lithium-ion capacitors. So you're adding some lithium-ion battery cathode material in there, trying to get the energy density up and yet retain the fast charge rate. So that work is ongoing. And again, this just shows some cycling data with those hybrid electrodes. And then here, this shows how the additive actually improves the cycling efficiency. If you look at the chart on the left there, the additive has a significant effect on charge-discharge efficiency of these systems. This just shows the actual discharge curves. I'll skip over that. And then just to conclude, the work that we're doing on lithium-ion capacitors is going to transition to fast charge batteries. So with the lithium-ion capacitor work, we found that we can really charge these cells very fast. For the larger cells that we're testing, these 200 farad cells, we're charging at 50C, so that's about a minute charge. And we can do this for thousands and hundreds of thousands of cycles. So that approach of having the oversized anode, hard carbon anode, is a valid approach that we can then apply to fast charge lithium-ion batteries. So just to finish up here, acknowledge who's done this work in the AR electrochemistry branch. myself, and the people that I mentioned at the beginning, and then some of my colleagues here at ARL. Richard Zhao specifically has done a lot of work on the lithium-ion capacitors, and Sam Delp. We've been working with Jim Zhang at Florida State University on these lithium-ion capacitor systems, and General Capacitor, who's providing essentially prototype cells for these tests. So, and we're also working with Dave Mitlin at Clarkson University, he's trying to develop some new carbons, hard carbons, for these anode materials. So, and then just some metrics, as we say. So, any questions?
Thanks, Jeff. We'll allow a minute here for any questions to come in.